All right. Happy day 41. Last real day of class. So we'll start with a song. Famous song by the Pixies, Here Comes Your Man, which apparently is inspired by the small earthquakes that the lead singer experienced as a teenager growing up in Southern California. And the third verse of this song is big shake on the boxcar moving, big shake to the land that's falling down. Is a wind makes a palm stop blowing, a big, big stone fall and break my crown. So, earthquakes can inspire art, but they can also inspire terror, since today we will be talking about earthquake hazards, okay? But last one of these logistics, all right? So this is the last lecture of the material where I'm presenting new material, okay? And there are only two things due on Sunday: the lecture quizzes from day 40 and 41. And that means there's no lab assignment and there's no reading quiz. I spent yesterday valiantly trying to vanquish Blackboard and get it as up to date as possible. And this is just a reminder that the Blackboard grade is not like what you see on there is not going to be exactly how I calculate the grades, because Blackboard is a black box and I want to make sure that I calculate your grades as correctly as possible. So what I actually do is once all the grades have been uploaded, I calculate them in Excel so that I can actually do the math, okay? So your grade, the weighted total should be close to what you have, but it is not your total final grade, okay? That brings us to the last grade that you'll get in this class, right, is our final, which will be a Blackboard exam that you will need to take next Thursday. And what I've decided to do is that I will make the exam available for a 12-hour window on Thursday from 9 a.m. to 9 p.m. You will have 2 hours to do it. So that means, right, you should not start any later than 7 p.m. on Thursday. And it'll be about 60 questions, and 66% of it, so about 40 questions, will be from the most recent part of the class, day 28 through 41. So that's everything from sediments and weathering up through earthquake hazards today. And then the remaining 20 questions on the exam will be related to material from earlier in the class, okay? You will only get one attempt on this exam, unlike the last one, okay? I think given how people did really on their first attempts last time, it should be okay, all right? So let's talk about studying. So here's kind of what I'm thinking. So this Friday, the very last official lecture of the semester, I will do a review of topics, okay? From that review, I will release a study guide similar to what I have done in the past on Friday afternoon. Then for office hours during finals week, what we are asking that you do is to just use the primary geology 001 team on Microsoft Teams. And the TAs and I will be available during the beginning of the week. Okay, so Emily will be available Monday from 10 to noon. I will be available from noon to 1. And then Tuesday, Hannah will be around 10 to noon. And then Wednesday, Kristen will be around 10 to noon. And I will be around noon to 1. I am supposed to attend a digital conference next week I was supposed to be in Vienna. I'm pretty bummed that I am not there. But, you know, attending a conference in the comfort of my tiny little bedroom is just as good as drinking beer in the streets of Vienna in the spring. What can I say? Anyway, so I am going to be a little busy next week, like trying to attend these conference things. But as always, if you message me on Teams, I basically respond to it at like the moment that I get it. So you can continue to do that. That's literally the best way that I'm available, and it's probably how I'm going to do this forever from now on. And then you can email me too. And then as sort of a study break, we're going to post the most creative Lab 10 assignments next week. And we'll, of course, ask for your permission if we think that yours should be shared, or if you yourself want to show what you did for your assignment with your classmates, let us know. But we had some really amazing displays of creativity, like an original song played on the ukulele, and a parody of a Bob Dylan song played on the guitar and sang. Some rewrites of classic children's books that were really funny, and lots of memes. Thank you guys. And so I just want you guys to be able to see the other work that your classmates did on this last assignment. So, all right, why don't we jump into the last new material of the semester? So we're going to talk today about earthquake hazards. And so when we think about hazards related to earthquakes, right, the first thing we can do is put on our geologist goggles, right, and look at where earthquakes occur, right? We know that they occur predominantly along plate boundaries, with bigger, deeper ones at convergent boundaries, whether that's a continental collision zone like the Himalaya or subduction zones in the Pacific Ring of Fire, or other collisional zones like in Southern Europe. But now let's take our geologist goggles off and put on our human goggles and realize that the hazards from earthquakes, right, aren't that the earthquakes happen, it's that earthquakes happen and humans live where they happen, okay? So the map on the left is where the earthquakes occur, and the map on the right is earthquake hazards, okay? Now, the most obvious thing that you can tell from this map is that we only map earthquake hazards on land, right? Okay, because humans only live on land. So we can begin to identify on hazard maps some of the risks that might be involved from earthquakes. So let's zoom in on North America, all right? So this map is showing the different areas of risk from earthquakes around the country, and we can identify just a few very broad patterns here, right? Is that first of all, we see that the Western United States, particularly along the Pacific coast, have the highest risk from earthquakes, along with this big zone in the middle of the heartland where the New Madrid earthquake happened in the early 1800s. So, and as well as the most extreme, really in the whole country, is in coastal Alaska, because it is along an active subduction zone. And actually one of the largest recorded earthquakes in history happened outside of Anchorage, Alaska in the 1960s. So these big areas of high risk, what are some other patterns we might notice here? Is that, well, These are places that are located along active faults. They are located along areas with high topography, okay? Or they are related along areas where there is a history of large earthquakes occurring, even if it's not in a tectonic boundary. And some of these places are like the New Madrid Fault area in sort of the confluence of the Ohio and Mississippi rivers. That's why those rivers actually converge there, is because this fault zone creates a local depression for the rivers to flow into. But then also, up here in New England, we actually have a moderate risk of earthquakes, particularly here in Vermont. And that's related to earthquakes that are happening in the boundary between the crystalline ancient bedrock of the Canadian Shield and younger rocks in the northern U.S. that cause earthquakes every so often, like the big one in Montreal in the 1730s. So now let's think about, well, okay, these are hazards, right? But now let's look and think about this more broadly, like in the US. All right, so we haven't really talked about this a lot in my class because it's not really the focus, but I don't think that natural disasters are really natural. Natural disasters are man-made disasters that result from natural events. So the way that you can think about it, right, is that old saying, like, if a tree in the forest falls, does anyone hear it, right? Well, if a tree falls in the forest, does it affect anyone? No. If a tree falls in a neighborhood and crushes someone's little house, yeah, then it affects people. Okay, so that's what we would consider a really small natural disaster. So now let's apply that kind of thinking to the United States and think about people, right? So if you have an earthquake that happens in the middle of the prairie in Nebraska, where there's very little population density, unfortunately, it might affect a small community, right? But if you have an earthquake that happens in Los Angeles, where there's tens of millions of people living, then that's going to have a much larger impact, right? So when we talk about earthquakes, we need to think about how the hazard evolves through time. So there's this really good movie. Once the semester has finally ended, and those of you who have missed out on spring skiing this year, there's a really great movie about the snowboarder Kevin Pierce, who was like the rival to Shaun White when I was in college, so 10 years ago. And so he was like the only person who was able to at all rival Shaun White's snowboarding abilities. But in the lead up to the 2010 Olympics in Vancouver, during a training run in a half pipe, Kevin Pierce had a devastating fall where he hit the deck of the half pipe and had a traumatic brain injury. And so kind of the point of this movie was that it was about how devastating the recovery is from a really traumatic event. And so, we are probably all of us are like this, right? Where if we see a car crash, or if we see a crash on a ski, like pro skiing, or if we even see like a NASCAR crash, right? So, people love seeing that immediate, like, ooh, that's a really nasty fall or crash or something. And then you're driving along like on the freeway and you see that accident, and then you drive on and you stop thinking about it, right? And so the rest of the world moves on, right? But the people who went through that event have to deal with the aftermath. And often the rest of us do not see what that recovery or what the consequences of it was for those people. And I think that this is very similar to how humans think about natural disasters as well. So we can think about earthquake hazards, and really all earth science hazards, as having a cascading primary and secondary and tertiary hazard structure. So like a primary hazard during an earthquake is when it's actually going on, the shaking that could cause a building to collapse. This is an immediate threat to human health. But you could have a secondary hazard where if you had the shaking that ruptured a gas line that now has started a fire, right? Now you are at the whim of this out of control fire that could go on for days or hours after the initial event, right? So how do you get a fire department and emergency services to respond to putting out a fire after they are already stressed by helping people get out of collapsing buildings? And then let's think like even more long term, right? So if you had an earthquake that damaged an oil refinery, and now suddenly a bunch of oil leaks out of pipelines and storage tanks into the soil and into the groundwater, now you have an environmental threat that could persist for years to decades to centuries after the initial earthquake. And so the way that humans respond and mitigate these risks to these hazards often shapes how communities and cities and countries are built after really watershed events. Okay, so let's talk about these main earthquake hazards, right? So we have ground shaking and displacement, landslides, sediment liquefaction, fire, tsunamis, and then as a geologist, another consequence of earthquakes is that we get a lot of bad Hollywood movies made about them, like San Andreas, which is very bad. But anyway, so let's talk about ground shaking. Is if you have an earthquake where the fault slip ruptures to the surface, it will create offset, right? So I've shown you this picture already of what they called the Great Wall in Kaikoura, New Zealand, where an earthquake thrust up this fault scarp and exposed this fault scarp, right? And you can see it's probably about like 8 to 10 feet tall. But all right, so that's in the middle of a field. All right, so that's not really that, okay, maybe it broke a farmer's fence and they have to go out and fix the fence. Ultimately not that bad. All right, what if you have fault rupture that goes up to the surface underneath your house or your office building? All right, now you have a problem because now someone's shelter and livelihood is threatened. Now, what if we know from previous lectures about faults, right, is that they often occur in low-lying areas, right, in valleys. And where do humans like to build reservoirs? Across valleys. So what if you have slip along a fault where there is a dam or reservoir? In Taiwan in 1999, there was a big megathrust earthquake that caused 9 meters, okay, so about 30 feet. This is a 30-foot shift in ground elevation on a dam. So what happens to that dam when it has been literally snapped in half? The water rushes out of the dam and it could devastate literally everything in the valley below. Okay. All right, so that's surface rupture, but what about the actual ground shaking, right? So we know that the primary characteristics of earthquakes is the arrival of P waves, then S waves, and then surface waves. And what we need to think about here is how quickly does changes in that shaking happen. So in 2017 in Mexico City, there was a large earthquake that was quite devastating. Right, so these earthquakes can be quite dangerous when you have ground shaking, particularly in places like Mexico City that are built on a former lake bed. It can cause a lot of intense shaking, and if buildings are not constructed to be resilient and adaptive to seismic activity, then they could collapse. Right, so relating this back to our different seismic waves, right, is the type of shaking you experience from each wave, right? So P waves are that like force push of compressive energy, and so that can cause vertical vibrations. Now, typically that is not as damaging as S waves and surface waves because it's just compressive, whereas S waves and surface waves have a shearing component to them, causing stuff to wiggle back and forth like jello on a plate, right? And so what happens with the primary and secondary waves is sort of that up and down and side to side. But what is really damaging is when you have the surface waves arrive. And so the Rayleigh waves, or the Love waves, sorry, cause stuff to go back and forth like this, right? So you are kind of ripping stuff apart. And then the Rayleigh waves are those which are the undulating waves. So that's like, you know, waves you'd see out at the ocean, like that type of motion. And if infrastructure is not built to withstand these different types of shaking, you can get devastating consequences, right? So depending on how we decide to build different structures, whether that's office buildings, homes, or roads, right? The type of shaking that happens could cause it to collapse in a way that's quite devastating. So now, an interesting thing about earthquakes is that the intensity of ground shaking, right, is not just limited to the actual fault, right? So the intensity of ground shaking is affected by the topography and the bedrock soil type and how close you are to the active rupturing fault. So here is a map of earthquake hazard from California, with the pink colors being the highest zone of risk. Okay, so the most obvious feature that we can see here is that these hazards line up with the position of the main San Andreas Fault and the ancillary faults that occur along it. Okay, but what we also see is that in areas of like the San Francisco Bay, right, in the valley, as well as the low-lying parts of Los Angeles and the valleys in the surrounding area, is that we have really high hazard. So let's think about a question here. What is more dangerous? Is it more dangerous to be in a river valley or on top of a mountain during an earthquake? Okay. So the intensity of ground shaking can be amplified through different bedrock and soil types. What I mean by this is, think of a thought experiment, right? If you have a rigid, like basically a brick, right, and you shake it back and forth, it doesn't jiggle, right? You get out some jello and shake it back and forth, that motion is accentuated. And so taking this back to geologic materials is that if you have solid bedrock versus unconsolidated sediment, these surface waves can change in their velocity as the seismic energy is released. So this can cause intensified ground shaking in areas of unconsolidated sediments, like river valleys or valley bottoms, where alluvial sediment, so river sediments, have filled in the valley and it's unconsolidated. Right? So if we think about an imaginary landscape where we have bedrock and then a river valley and then bedrock and then coastal marine sediments, which are also unconsolidated, the amount of ground shaking in these unconsolidated areas is going to be much more intense than anywhere built on bedrock. So let's go back to California, right? So let's zoom in on Los Angeles. So huge city, right? That is completely urbanized, right? If you have been there, right, it's kind of remarkable just how humans have figured out how to build something on almost every single available slope. So what is interesting about like the development of Los Angeles in the last 100 years or so is that it used to be a semi-arid Mediterranean environment where there were dry stream beds that would sometimes become active with rainstorms and flow out towards the ocean. But as millions and millions of people moved into LA in the 20th century, they urbanized everything. And so they built entire cities over former locations of streams, and then they built man made rivers to drain the water out of the mountains. And so what you end up with here is this like really sort of weird socioeconomic and class and um, like largely level social problem related to geology and threats from earthquakes and landslides. So where are the most expensive homes in LA, right? Think of like the Kardashians and all the Hollywood stars. They all live in the Hollywood Hills, right? They live Beverly Hills. They live on bedrock slopes. All right. The most densely built, densely populated parts of Los Angeles are in the valley bottoms, the former stream valleys, where people typically have less money, right? They have less means to rebuild their lives if something were to happen to them, and the threat from earthquake shaking is exaggerated in those low-lying areas due to the acceleration of surface waves during an earthquake, right? So it's an interesting sort of outgrowth of how humans have decided to populate and build in LA, and the sort of like background geologic hazard that is always present there. Okay. So the next hazard that we want to think about is what happens in unconsolidated sediments that are saturated with water. So when you shake partially saturated soil or saturated soils, it can cause a phenomenon known as liquefaction. And this is where the initially loosely packed grains, so these sand grains with water in between them, right, suddenly are agitated, and now the pore space becomes much larger between individual grains, and it causes the soil to then behave like a liquid, right? This can cause like truly devastating results that turns solid earth or soil into basically a swirling mess. In Indonesia, a few years ago, there was a really bad liquefaction disaster in a community, and this shows footage from that event.
turns into a liquid-like substance. And what that does is it causes building collapses, it also generates landslides, and information.
Locals in Palu can hardly recognize the neighborhood. Where Survivor's house used to stand is now a cornfield that once was a mile away. It's lit here like an urban rag after the land turned green. A partial road was broken apart and carried away, along with shops, homes, and everything else. The death toll from the disaster keeps rising. These 5,000 people are still found missing. In Venezuela, residents salvaged some of their belongings, but rescuers knew that one body after the sweltering heat. A third was recalled and searched for life under the rubble. These surviving residents were already had to suffer.
So liquefaction is an extremely dangerous hazard from earthquakes, and it often occurs in places where there are like large rivers that are flowing nearby or along the ocean. And I know in the first lecture about earthquakes, we talked about San Francisco. What type of soil do you think there is in um, the market district of San Francisco? Marine sediment. Where are the largest buildings built in San Francisco right now? In the area with the highest risk of liquefaction. Can you imagine what would happen to that city if liquefaction were to happen similar to what happened in this town in Indonesia? It would be incredibly devastating, right? So this is a very, very dangerous part of earthquakes that is frankly difficult to predict exactly how it's going to happen, okay? And when it does, how do you respond to that, right? You have to wait until it's finished, right? Anyway. So the other thing, right, is let's go away from the valley bottoms and up onto hillsides, right? So even though bedrock slopes, where your house is built with a foundation directly into solid rock, that might be safer. But if you have loose sediment on a hillside and then you shake it, right, you're going to cause landslides. And so during big earthquakes, you can get really intense landsliding events in mountainous regions. So I'm not going to try to pronounce, I'm sorry, I don't know how to pronounce that word, but in eastern China, there was a magnitude 7 earthquake that if you look at the before satellite image of this forested landscape, right? And then after the earthquake, you can see all these light colored areas are scars from where from earthquake induced landslides sent material down the hill slopes, devastating the forest in the way. Okay. Now, if we go to our favorite place of New Zealand, right? A earthquake in Kaikoura, which I've alluded to a couple of times, right? Where you had a magnitude 7-8 earthquake, which is quite large for New Zealand, caused an immense amount of landsliding in the coastal mountains here, right? So there aren't a lot of cities located in these mountains. It's too mountainous to actually build much there. But what it does do is if you have a landslide and the only road into your town is now suddenly covered in like 30 feet of rock and boulders, how do you get stuff into the town, right? Now, another threat that can happen from earthquake landslides is that if you have a big landslide off of a slope that sends material down into the valley, like here you can see this active scar and all this material down here, and it dams a river, right? Then you get a lake that builds up behind it. What if suddenly this earthen dam from the landslide debris suddenly fails? Then you have a gush of water out of that dammed lake, especially if an earthquake destabilizes this. Okay. All right, now let's go to sort of the largest scale threat from earthquakes, and that is tsunami. So a tsunami is a long period, meaning there's a large wavelength, low amplitude, meaning it's initially not a very tall wave, that is generated by the displacement of a volume of water. All right. So this means that if you suddenly pulse water, like if you're in a swimming pool, and you like make a boil of water by going like this with your hands under, right? You cause a boil of water to come up to the surface and it goes out, right? Because you are displacing the water with the movement of your hands. So a tsunami is when we have a displacement of water caused by either surface rupture from a fault on the bottom of the ocean, or a volcanic explosion and landslide, or a release of gas from a volcano, or a landslide into the ocean, right, or into a body of water, or if we have a meteorite impact where you basically are doing a cannonball into the ocean. All four of these types of processes can generate a tsunami wave. So this diagram shows what this looks like at its origin point in the ocean, right? So this is an example of a earthquake-induced tsunami where surface rupture on the fault, right? This part of the fault gets bulged up, and during that displacement, during that movement, it displaces the water above it, right? And it sends energy up, and then that water turns into a low amplitude, low period, or long wavelength, or long period, long wavelength wave that emanates out from that point, and then it is, moving in radial direction away from where that fault was. Okay, so if you have fault displacement in a coastal area, the near field tsunami is the one that can be quite dangerous. Okay, right, so tsunamis are different than large waves driven by wind. Right, so if you've seen any of those videos of the really crazy surfers off the coast of Portugal or in Hawaii when they're surfing like 40 and 50-foot waves, those are from wind, from like continuous pulsing of strong winds that causes these tall waves with relatively short wavelength, or the distance between each crest of the wave. Okay, those can cause some coastal flooding, right? So like you could think of as during a like a hurricane or even a nor'easter, right, here in the Northeast. Whereas during a tsunami, you have one very large pulse of energy that's coming towards the shore, and in order to accommodate this sort of like rise in the water back here and the pullback in of the waves towards the ocean, it causes a like large scale like draining of a beach. So stuff that is typically below sea level can become exposed in the run up to a tsunami. And as the tsunami approaches the shore, the energy in the wave gets compressed, right? Because it's more shallow, and then the wave height increases. That incredible amount of water then will inundate much further inland. Right? That is why tsunamis are so devastating, is because a really large volume of water traveling at a rapid speed can go much further inland than we are normally prepared for. So I'm not going to really show videos of the landward inundation from the Tohoku tsunami in 2011, but this video shows what it looked like as the tsunami was coming on shore. And now you're seeing the bulge of water that is coming up over that breaker, right? This is this is like still terrifying every time I watch these. Right? And it's not just one wave and it's over. It just keeps going inland. All of that energy is moving that pulse of water in towards land. Right? This is not like a wave that you are used to on the beach. It is just a non-stop deluge. So this is from that same area in Sendai, Japan. You can actually see that that video, I think, was taken from a pier right up here, and you can see the breakers that are right there. And this is a false color satellite image where the colors, so that you can understand them, the red is vegetation, and the blue is obviously water, and then the gray here is the built environment. So that's where buildings and stuff are, okay? So this is a image taken in 2008 before the tsunami, and here is the day after, right? So what you notice here, right, if we go back and forth, we can see that there are large swaths of these cities, right, that are completely inundated with ocean water from the tsunami, right? It's quite jarring to think about just how devastating this is, right? The water made it all the way up to here. Okay. So that's the near field effect of a tsunami, but let's think about what happens far field. Okay, as tsunamis are generated, they expand out and dissipate energy through the ocean in every single direction. So this is what happened from that same tsunami as it traveled across the entire Pacific Ocean. It looks like you dropped a huge rock in a pond, right? And there's big ripples. As those ripples of energy are, expanded across the ocean, they refract where they hit obstacles like other land masses or islands, and they also interact with bathymetry, so the elevation of the seafloor. And it goes across the entire ocean. And so during the 2011 earthquake in Japan, the tsunami was most devastating in coastal Japan, but there were smaller scale tsunamis along all of the coastal regions of the Pacific Ocean. And in fact, this tsunami even caused icebergs in Antarctica, which isn't even shown on this image, to break off of an ice shelf and out into the ocean, right? Because it was such a change in surface level and energy moving through the ocean. So now the colors show the amplitude of the wave, right? So with distance, the amplitude decreases, but we can still see here that there was a tsunami that hit all of these coastal regions of the Pacific Ocean. Right? So this was a truly catastrophic geologic event that hopefully no human will have to endure again in our lifetimes. Okay, so how do we mitigate the risk from earthquakes? Right, so we can set up tsunami warning systems, and we can also have now with cell phones like an easy way to reach everyone by sending out the warning that a primary wave has arrived, right? Because that happens first. And there will be a delay between when the primary and then the secondary and surface waves arrive. That gives you enough time to find shelter or to get away from like an unstable cabinet full of books, or like if you're in a liquor store, to get away from a bunch of glass bottles that could come and shred you. Okay. I'm not going to show this because we are almost out of time. You can also build infrastructure to be more resilient. So buildings that can withstand intense shaking, right? If they're actually, if they're built to kind of go with the flow of an earthquake and not collapse. We can also create automatic shutoff valves in gas and water lines that, if there is shaking during an earthquake, they trigger and prevent the release of gas or water, and thereby reducing the risk of a water shortage or even more damaging, a fire. Right. So the worst consequences from many earthquakes is not the shaking itself; it's the fire caused by damage to gas lines afterwards. Okay. I won't show this either because we are out of time. And finally, you cannot predict an earthquake. Right? There are some things that might happen ahead of one. Right? You might see deformation of the ground surface, meaning that elevation could change or tilted. In rare cases, there's foreshocks, so smaller earthquakes that lead up to a bigger earthquake. You could see changes in water levels in groundwater wells. You could see the emission of radon gas, or even sort of the folklore of animals behaving weirdly because of some change in low amplitude energy that only they can detect. But none of them are definitive, and some of it is kind of pseudoscience. So really, the only thing that we can do, just like with flooding, is we can look at earthquake recurrence intervals where the slip along certain active faults can sometimes have a periodicity to them. And just like we did with flooding, you can look at the occurrence of earthquakes in the past and use that to give an idea of how likely it is that a certain magnitude earthquake that could occur in the future. Okay. All right. Sorry, that was a little bit longer, but powered through, and I'll see you guys on Friday.